After studying this module, you will be able to know the concept of limits and continuity, know the rules of for limit and the properties of continuous functions, learn about the limits of a sequence.
A limit is the value that a function approaches as the input or index approaches some value. The concept of limit is essential to calculus and is used to define continuity, derivatives, and integrals. The concept has wide applications in analysis of various economic phenomena. Suppose f is a real valued function and a is any constant, then we write limit x tending to a fx is equal to capital A, or fx tends to a as x tends to small a, where tending to stands for tending towards but is not equal to. This implies fx tends to or gets close to capital A as x approaches or gets close to small a, not necessarily equal to a. This means that we can make fx as close as possible to a as we want for all x's sufficiently close to small a. It is possible, however, that the value of fx does not tend to any fixed number as x tends to small a. Then we say that limit x tending to a fx does not exist, or that fx does not have a limit as x tends to small a.
Let's take an example to understand limit. In the table, we have shown the value of the function corresponding to the value of x close to 3. As x tends to 3, it seems that 3 into minus 2 tends to 7. So, 3 into minus 2 is equal to 7. If x is precisely equal to 3, then 3x minus 2 is equal to 7. But the definition of 3x minus 2 ignores the value of 3x minus 2. Let's take an example to understand the concept of limit. Show that limit x tends to 0x sine 1 by x is equal to 1 by x is equal to 0. Let's try to solve this. Now, modulus x sine 1 by x minus 0 is equal to modulus x sine 1 by x is equal to modulus x into sine 1 by x is less than equal to modulus x. Let epsilon greater than 0 be given. Choose delta is equal to epsilon, then modulus x sine 1 by x minus 0 less than epsilon when 0 less than modulus x minus 0 is less than delta. Hence, limit x tends to 0x sine 1 by x is equal to 0. Let's discuss limit with the help of this example. We need to show that limit x tends to 0 sine 1 by x is not equal to 0. Now, to solve this, let epsilon is equal to 1 by 2 greater than 0. Let delta be any positive number. Now, 1 by delta greater than 0, therefore there exists and belongs to natural number such that n greater than 1 by delta. This implies 2 and pi plus pi by 2 greater than 1 by delta, or 1 by 2n pi plus pi by 2 is less than delta. Let x is equal to 1 by 2n pi plus pi by 2, then 0 less than x minus 0 less than delta. Now modulus sine 1 by x minus 0 is equal to modulus sine 2 and pi plus pi by 2 is equal to 1, which is greater than epsilon. Therefore, for epsilon is equal to 1 by 2 greater than 0, such that for every delta greater than 0, there exists some point x is equal to 1 by 2n pi plus pi by 2, for which modulus sine 1 by x minus 0 is greater than epsilon and modulus x minus 0 is greater than 0 but less than delta. Hence, limit x tends to 0 sine 1 by x is not equal to 0. Another formal definition of the limit of a function can be given as a function f(x) is said to approach the limit a as x if for any positive number epsilon, howsoever small, we can find a number delta such that f into x minus a is less than epsilon for all values of x satisfying x minus a is less than delta except possibly at x is equal to a. Geometrically, a function is continuous if its graph is connected, that is, it has no breaks. On the other hand, if the graph makes one or more jumps, it is said to be discontinuous. Definition of a continuous function: let f be defined on a domain that includes an open interval around a, then f is continuous at x is equal to a provided that fx tends to fa as x tends to a. F is continuous at x if fx is equal to fa. Hence, we see that in order for f to be continuous at x is equal to a, the following three conditions must be fulfilled. The function f must be defined at x is equal to a. The limit of fx as x tends to a must exist. The limit must be exactly equal to fa. Roughly speaking, a function is said to be continuous if small changes in the independent variable produces small changes in the function values, otherwise it is said to be discontinuous. Let us define discontinuous function. Let f be a function such that a and b in closed interval tends to R, and let c belong to a and b in open interval. F is said to be discontinuous at C if it is not continuous at C. For f to be discontinuous at C, there are many possibilities, namely, limit x tends to C from below fx does not exist, limit x tends to C from above fx does not exist, limit x tends to C from below fx and limit x tends to C from above fx, limit x tends to C exists but fc does not exist. Limit x tends to C fx and fc both exist but limit x tends to C fx is not equal to fc. F is said to have discontinuity of the first kind at x is equal to C if limit x tends to C from below fx and limit x tends to C plus fx both exist but are not equal. F is said to have discontinuity of the first kind from left at x is equal to C if limit x tends to C from below fx exists but is not equal to fc. F is said to have discontinuity of the first kind from the right at x is equal to C if limit x tends to C from above fx exists but is not equal to fc. F is said to have discontinuity of the second kind from the left at x is equal to C if limit x tends to C from below fx does not exist. F is said to have discontinuity of the second kind from the right at x is equal to C if limit x tends to C from above fx does not exist. F is said to
Let us discuss an economic application. Examine the demand curve P is equal to A upon x plus B, where A and B are positive constants. Show that demand increases from 0 to indefinitely large amounts as the price falls. What type of curve is the total revenue curve? Show that the total revenue increases to a limiting value. Draw the graphs of demand and total revenue curves to support your argument. Since we have to examine the behavior of demand as price is changing, we write x plus b is equal to a upon p, or x is equal to a by p minus b. The demand equals 0 when price is equal to a by b. For small prices, it is given by x is equal to limit price tending to 0, a upon p minus b is equal to infinite. On combining the results of these two limits, we can say that demand increases from 0 to indefinitely larger amounts as price falls. We can write total revenue curve as P into X is equal to AX upon X plus B. Further, limit X tending to infinity, total revenue is equal to limit X tending to infinity AX upon X plus B is equal to limit X tending to infinity A upon 1 plus B by X. This is equal to A, which implies that total revenue curve increases to a limiting value A. To draw the graph of this demand curve, we note that there is a rectangular hyperbola with center as minus b comma 0 and asymptotes parallel to the axis. Since A is greater than 0, the two parts of the curve lie in the first and the third quadrants, formed by the asymptotes. The part AB of the curve, where X and P both are positive, is the relevant part of the demand curve. As shown in the figure, we can write the total revenue function as TR x plus b minus AX is equal to 0, or TR x plus b minus A into x plus b is equal to minus AB, or x plus b into TR minus A is equal to minus AB. This is the equation of rectangular hyperbola with centers as minus b comma 0 and asymptotes being parallel to the axis. Since right hand side of this equation is negative, the two parts of the curve are lying in the second and the fourth quadrant, formed by the asymptotes. The relevant total revenue curve is where TR and X both are positive, as shown in the figure.
To have a removable discontinuity at x is equal to c, if limit x tends to c, fx exists but is not equal to fc. Intermediate value theorem: if a function f is continuous on closed interval a and b, and x1, x2 belongs to closed interval a and b, x1 is less than x2 such that fx1 is not equal to fx2, then f takes every value between fx1 and fx2 somewhere in the interval x1 x2. Suppose fx1 is less than fx2 and fx1 is less than k, which is less than fx2, then intermediate value theorem says there exists C belongs to x1, x2 such that fc is equal to k. If f is not continuous on closed interval, then the conclusion of above theorem may not hold. Let us discuss an example to understand the concept of continuous function. Let
The intermediate value theorem. An important reason for introducing the concept of continuous function is to distinguish between continuous and discontinuous graphs. That is, graphs, those are connected, and those with more jumps and breaks. For this, the continuous function follows the theorem which states that suppose a function f is continuous on a closed interval a comma b if y0 be a number between f of a and f of b, then there exists a number small c in the closed interval a comma b such that f of c is equal to y0. A useful implication of the above theorem is in finding the roots of a polynomial of degree greater than 2. This theorem tells us that if f is continuous, then in any interval a comma b on which f of a and f of b are on different signs must contain at least one small c such that f of c is equal to 0.
Gx is equal to cos x for all x belongs to R, we have to show that G is continuous on R. Solution: let C belong R, then modulus Gx minus Gc is equal to modulus cos x minus cos c. This equal to modulus minus 2 sin x plus c by 2 into sin x minus c by 2 is equal to 2 modulus sin x plus c by 2 into modulus sin x minus c by 2. Now, since modulus sin theta is less than equal to 1, modulus gx minus gc is less than equal to 2 modulus sin x minus c by 2 or 2 modulus x minus c by 2 as modulus sin theta less than modulus theta. Modulus gx minus gc is equal to modulus x minus c. Let epsilon greater than 0 be given. Choose delta is equal to epsilon, then modulus gx minus gc less than epsilon when 0 less than modulus x minus c less than delta. Therefore, G is continuous at C. As C is arbitrary, therefore, G is continuous on R.
Let us now summarize what we have learnt in this module. If a function f is defined for all x's near to a but not necessarily at x equal to a, then we say that f of x has a limit. A as x tends to small a if f of x tends to capital A as x tends to small a, but not equal to small a. We write limit x tending to a f of x is equal to capital A or fx tending to a as x tends to small a. A function f is continuous at x equal to a provided that f of x tends to f of a as x tends to small a. F is continuous at x tending to a if limit x tending to a f of x is equal to f of a. Continuity implies that there are no breaks, no jumps in the function and it is a smooth graph. Intermediate theorem under mathematics uses continuity as a precondition.
Let's now discuss the rules for limits. Suppose that f and g are functions defined in the neighborhood of a but not necessarily at a. Then we have the rules. If fx when limit x tends to a is equal to a and gx when limit x tends to a is equal to b and c is a constant, then first limit x goes to a into cf into x is equal to c limit x goes to a fx is equal to c into a. We can factor a multiplicative constant out of a limit. Limit x goes to a fx plus minus gx is equal to limit x goes to a into fx plus minus limit x goes to a into gx is equal to a plus minus b. Limit of sum or difference of two functions is the sum or difference of their individual limits. limit x goes to a into fx into gx is equal to limit x goes to a fx into limit x goes to a gx is equal to a into b. Limit of product of two functions is the product of limits of their individual function. Limit x goes to a fx upon gx is equal to limit x goes to a fx divided by limit x goes to a gx is equal to a upon b, provided b is not equal to 0. Limit of ratio of two functions is ratio of the limits of individual function. Limit x goes to a fx to the power of n is equal to a to the power of n if a to the power of n is defined. Compute the following limit x square plus 5x limit x tends to minus 2. Using the rule of addition of limits, fx plus or minus gx limit x tends to minus 2 is equal to fx limit x tends to minus 2 plus or minus gx limit x tends to minus 2 is equal to a plus or minus b. We get x square plus 5x limit x tends to minus 2 is equal to x into x limit x tends to minus 2 plus 5 into x limit x tends to minus 2, which is further equal to x limit x tends to minus 2 into x limit x tends to minus 2 plus 5 limit x tends to minus 2 into x limit x tends to minus 2. So minus 2 into minus 2 plus 5 into minus 2 equals 6. Limit of a sequence. Let a1, a2, and so on be a sequence of real numbers. We say that a finite number L is the limit of this sequence if for any arbitrarily chosen small positive number e there exists a positive number n such that for all x is greater than equal to n we have ax minus L less than epsilon. This is also written as ax limit x tends to infinity is equal to L. If ax limit x tends to infinity is equal to L finite number, the sequence is called a convergent sequence. Example, ax is equal to x plus 1 by x. Various members of the sequence are 2 upon 1, 3 upon 2, 4 upon 3, so on, 101 upon 100, 1001 upon 1000, for x is equal to 1, 2, so on. We note that as x becomes larger and larger, the successive terms of the sequence become closer and closer to unity. Thus, x plus 1 by x limit x tends to infinity is equal to 1. Hence, the sequence is convergent. If ax limit x tends to infinity is equal to plus or minus infinity, the sequence is termed as divergent sequence. Example, ax is equal to x minus 1 by x. Various members of the sequence are 0, 3 upon 2, 8 upon 3, 15 upon 4, and so on. We note that as x becomes larger, the successive terms of the sequence also become larger. Thus, x minus 1 by x limit x tends to infinity is equal to infinity and the sequence is divergent. Let's now discuss the properties of continuous functions. If f and g are continuous functions at a, then a, f plus g and f minus g are continuous at a, b, f into g is continuous at a, c, f by g is continuous at a if g into a is not equal to 0, d, fx raised to power p by q is continuous at a if fa raised to power p by q is defined. Composites of continuous functions are continuous. If g is a continuous function at x is equal to a and f is a continuous function at g a, then f g x is continuous at x is equal to a. Let's now discuss how we can apply the concept of continuity in economics. Suppose a firm faces the following demand function for its output: 12 minus p for p greater than equal to 0 less than equal to 8, x is equal to 20 minus p for p greater than equal to 8 less than equal to 10, z for p greater than equal to 10. We have to graph this demand function with p on the vertical axis and x on the horizontal axis and find the value of output at which the demand curve has a kink. Also, we have to write the firm's revenue as a function of output and graph this function. LHL is equal to 10 into 4 minus 0.5 into 16 is equal to 32. RHL is equal to 12 into 4 minus 16 is equal to 32. TR4 is equal to 10 into 4 minus 0.5 into 16 is equal to 32. Therefore, TR is a continuous function. Example: show that the following equation has at least one root in the given interval x cube minus x is equal to 5 in 0 2. Solution: let fx is equal to x cube minus x minus 5. Then f0 is equal to minus 5 is less than 0 and f2 is equal to 8 minus 2 minus 5 is equal to 1 is greater than 0. Hence, by intermediate value theorem, there exists a number c belongs to 0 2 such that fc is equal to 0.